Welcome to the second session of day 4. So with us we have Dr. Clint George, who is an assistant professor in IIT Goa. He in the School of Mathematics and Computer Science, so basically my school. He obtained his PhD and Masters of Science from the Department of Computer and Information Science and Engineering at University of Florida. And he completed his BTech in Computer Science and Engineering from College of Engineering, Trivandrum. He works primarily in the area of machine learning and applied statistics, which includes topic models, empirical-based methods, Markov chain, Monte Carlo and variational inference methods, and cancer genomics. So with this, I would like to welcome Dr. Clint George to the session, and over to you, Clint.
Hello, Sharad, am I audible?
Yes, you are.
Oh, okay, thank you. Yeah, thank you for the introduction. So I can start this session now, right?
Yeah, you can start.
Oh, okay, yeah. So good afternoon, everyone. So I think, I don't have to say my name because I'm already introduced. So I'm an assistant professor in the CS department in IIT Goa, and I work in the area of machine learning. Okay. And today my plan is to talk a little on machine learning and how machine learning can be clubbed with IoT devices for helping agricultural industry. Okay, so I just stop me anytime if you have any questions. So I hope you can see my screen. Okay, yeah. Okay, so just 1 second. Yeah, I will start with a video. Okay, so this will motivate you to the idea of precision agriculture and how machine learning or AI can help in the precision agriculture. Okay.
So Clint, you need to share the system audio when you are sharing your. You need to share system audio because the audio from the video will not be heard otherwise.
Okay.
So when you share your slide again, and then at the top you will see include system audio.
Okay. So this doesn't have.
Not there. So you stop sharing.
Okay.
Then go to the share button in the control panel in Microsoft Teams.
Okay. Yeah.
Now when you click on share button, then you will see the different windows that you can share. On top of that, you will see include system audio.
Oh, okay. Thank you. Yeah. So let me just play this again. So now this is fine.
Over the next 2 decades, a technological wave will revolutionize the efficiency of farms all over the world. It can't come.
Yes.
By the year 2050, the human population will be nearly 10 billion, which means we'll need to have doubled the amount of food we now produce. This is an examination of the agricultural innovations coming down the pipeline that will help get us there. The industry has undergone major developments over the last century. 100 years ago, farming looked like this. Today, it looks like this, and tomorrow, it'll look something like this. These changes have allowed many of us to do other things with our lives. In 1900, about 11 million agricultural workers produced the food for 76 million people. Today, just 6.5 million workers feed 321.4 million Americans. 2 factors were most responsible for this surge in productivity: engines and the widespread availability of electricity. Today, the innovations on our immediate horizon include autonomous pickers, UK researchers have already created one that gathers strawberries twice as fast as humans. The challenge will be creating robotic pickers that can switch between all kinds of crops. Robots or drones that can precisely remove weeds or shoot them with a targeted spritz of pesticide, using 90% less chemicals than a conventional blanket sprayer. For the organic farmer, they could zap the weeds with a laser instead. This could have a big impact. The UN estimates that each year, between 20 and 40% of global crop yields are destroyed by pests and disease. Tiny sensors and cameras will monitor crop growth and alert farmers on their smartphones if there's a problem or when it's the best time to harvest. The Bonnie Rob can take a soil sample, liquidize it, then analyze its pH and phosphorus levels all in real time. As a proof of concept for all this autonomous farming technology, researchers at Harper Adams in the UK plan to grow and harvest an entire hectare of barley without humans ever entering the field. Companies like Egg Robotics have already commercialized software that analyzes drone-captured infrared images to spot unhealthy vegetation. Then, like a real-life game of Sim Farmer, the grower is alerted on their device when a troubled area is identified. Machine learning is regularly improving the system's ability to differentiate between varieties of crops and the weeds that threaten them. Not to be left out, a company called Mavericks contracts 100 pilots to fly light aircraft that are outfitted with multispectral cameras on data-gathering missions over large farms throughout the country. For an even wider view, Planet Labs operates a fleet of CubeSats that take weekly images of entire farms from space to help monitor crops. Other companies are creating analytics software to act as farm management systems, allowing growers of all sizes to deal with this new tsunami of data. And the Farmers Business Network combines data from many farms into one giant pool to give its members the power.
Yeah, I will stop here this video.
Over the next 2 decades, a technological
Yeah, so in the video that I have shown, you might have seen how we can apply, various sensor technology and how this machine learning and data science related algorithms can help to pick something from the farms, and we can also use this drones, okay, drones for tracking animals. Then we can use it for pest infestation. We can use these drones to spray insecticides and all these things. Okay, and another area that you can think of, this robotic farming. So we have these robots, okay, that is deployed in the farm, and these robots can actually, we have seen some of these things aspects in the video itself. It can be used to weed in the farm, and it can also be used for plucking the fruits. Okay, so these are some applied AI area where you see the use of AI and machine learning in the agricultural industry. Okay, and another place where we can use these drones. Okay, so these drones are, we can have this the sensors or the cameras installed on the drones. Okay, and these cameras can take pictures of the field. Okay, and it can be used for the soil and crop monitoring. Okay, so these are some motivating examples I wanted to show you before I start the interesting aspects of AI and machine learning, where you learn more about the algorithms and how these algorithms can be used for some of these useful applications. Okay, so I'm just going ahead. If you have any questions, just let me know. Okay. So far we have looked at this flying IoTs or drones. Okay, so this traditional crops scouting. Okay, it's a very time-consuming task. Okay, and it is very labor-intensive, and because this is mostly done through humans, it can be error-prone. Okay, but with the help of these drones, and with their reach, okay, we can cover a large area. Okay, that the data that is collected can be used for measuring plant health. Then we can use it for counting the and also we can measure whether the the plants are growing well. Okay, and we can also use it for an optimized farming setting. Okay, and we can another application of this flying drones or flying this is, I mean, we can use it for early detection of plant stressors. Then I mean, some of these things we have already seen. Then we can also use this idea in identifying damage fencing, and when they have when there is like a storm or something happened, right? So these things can be evaluated with the help of this the drones. Okay, and I also wanted to point out that along with these drones, we can also think about deploying small sensors which are connected through a network. Okay, and which can also help you to get continuous monitoring of the field. Okay, this can also help improve the planned monitoring and how we can I mean, avoid stress in the farm industry. Okay. So when we think about, I mean, and I also wanted to say that, I mean, in today's discussion, I wanted to focus more on this drone-based IoTs that can be deployed in a precision agriculture setting. Okay, so in this context, I wanted to explain this as an architecture where we have a sensor and we have a cloud-based architecture. Okay, and these are deployed to improve processor performance on edge devices, and also we are interested in maintaining low power consumption and also this small form factor. Okay, and so this includes, I mean, if you think about this architecture, we can think about there are 3 areas that you can think of. Okay, so one is the data collection. So this data collection is typically done at the sensor level or via the drones. Okay, and you can think about this multispectral data so that you collected over a field. Okay, so this can be this RGB channels. Along with RGB channels, you may also collect other information. For example, lidar that can be used to sense the depth of the field and other things. Okay, these things are mostly useful when you think about the tree canopy or other things, other factors of the field. Okay, so once you collected the data, you can have something like an interaction or the communication network that can be used to store this data in a cloud environment. Okay, and you can consider a system where we do all the data processing and analysis at the cloud setting. Okay, and in the end, once you have collected all these data and the historical data that you have collected in the previous the screening operations, right? So that can be used to predict what is the output that you can get from a field, or you can use it for an optimized planting or something like that. Okay, and this can be considered as a module called actions and reports. Okay, so this actions typically includes the actions that you take based on the algorithms that you develop based on the data. Okay, and this can be used to used for navigation on the field. Okay, and also to make the movements of the robots that you deploy on the field. Okay, and you can also consider that you have an interface where the farmers can look at the reports that you have generated with the help of the data collected, which can be used for future planning and also for some policy making. Okay, so these are some aspects of precision agriculture where you can think, I mean, the IoT can be deployed and that will help the betterment of farmers. Okay. So here I have classified this data collection as one block. Then this cloud data process and analysis as the second block, and we have this actions and reports. Okay, and in my presentation I wanted to focus more on and analysis. Okay, so this involves various machine learning algorithms that make use of images or other kind of data that you can think of. Okay, and how we can use it for classifying. For example, you are looking at apples. Okay, and you would like to pick the apple that is ripened, right? So you can think about an algorithm that you can that you can use to say the robot that this apple is good enough to pluck. Okay, so you can use it that use that way. Okay, so we will see. What kind of algorithms that we can deploy in a setting like that. Okay, and I will also talk about some practical aspects in the end where we can use the existing frameworks out there that can be deployed in an edge environment. Okay, yeah. So in today's lecture, I focus more on data processing and analysis. Okay, and I first wanted to point out what are the key areas or the key algorithms that you can think of in a setting like this. Okay. So I wanted to start with this crop area detection and condition analysis. Okay. So if you consider about this particular problem, right? So this involves mainly two steps. So the first step is the segmentation of the field. The segmentation of the field may be based on the remote sensed images that you have collected with the help of the aerial autonomous devices. So that can be drones or the aerial, aeroplanes. Okay. So here I have some examples on the right hand side. So you can see that there are different types of field that you can expect, and this is taken somewhere in the US. Okay, and you can see that in India, this setting can be quite different. Okay, so here people may grow different plants together. Okay, in a setting like that, you may have to adapt your algorithm accordingly. Okay, so if you consider this this detection problem or condition monitoring problem, so the first thing is the segmentation. By segmentation, what I meant is that I wanted to have so when you consider an image like this, you see that this area, it has a different color that is used for planting a type of plant. Okay, and this is for another plant. Okay, so based on the images that you have, you should be able to segment these boundaries. Okay, so these boundary segmentation can be used to manage the area of the land that you use for plantation. Okay, and you can also use this for policy making. For example, the Ministry of Ministry of Agriculture, right? So they wanted to get an idea about a state where what kind of crops are grown. Okay, then without making use of the human labeled information or the human collected data, you can make use of the images collected with the help of drones, of this aerial devices like satellites or other things. Okay, and it can be used for segmenting the field, and based on the segmentation, you can also get an idea about the area a particular type of crop is planted. For example, if you are interested in identifying the crop rice that is cultivated in Goa, for example. Okay, then you can look at these images, and the segmentation algorithms can be deployed to get an idea. Okay, so that is one aspect that you can think of in this particular example. Okay, then the other step that you have to keep in mind is we are interested in identifying which crop it is. Okay, or we are interested in seeing whether the crop is growing well. Okay, so there are some diseases that you would like to detect from the images. Okay, so that is the recognition phase. Okay, so that you will see that some of the algorithms that you are specifically developed for the segmentation phase, other set of algorithms are used for recognition phase, and which are also called as classification algorithms. And a typical machine learning classification algorithms can be applied in such setting. Okay. So let me just move on to other examples. So this is another project we have done recently. Okay, the idea is that so these are the arachnids. Okay, that is collected collected from the farmers in nearby areas of our institute. Okay, and so these arachnids are classified classified into different quality. Okay, for example, supari, Safed and Lal and other varieties. Okay, and the supari is the best variety that you can have. Okay, so this sorting of the arachnids is typically done with the help of human labors. Okay, so what we were trying to do in collaboration with the local the community is that we were actually thinking about deploying cameras. Okay, so these cameras can be used to take pictures of these arachnids. Okay, and these pictures can be sent to any of these deep learning or machine learning algorithms. Okay, so these algorithms will be used to just to classify the arachnids into one class or the other. Okay, so this way we can save time, and also it's a labor intensive job, so that can also be avoided. Okay, so this also come under the recognition algorithms or this classification algorithms that I have discussed in the previous slide. Okay, so now I move on to another two interesting aspects in the case of for example here we have an example for segmentation. Okay, so the segmentation of the images, for example, here we have an apple. Okay, that's an example. Okay, so one area of that apple is defective because of some disease. Okay, and for example, we are interested in identifying how much percentage of that apple is defective or something like that. Okay, so we can make use of this segmentation algorithm that you have seen in the previous slide, and we can use it to identify which area of the apple is damaged, and if the damage is more if you have to throw away that apple or not. Okay, so that is one decision that you can make. Okay, and you can also make use of this type of algorithms to identify what kind of disease that is occurring in these type of fruits. Okay, so that is one application that you can think of with the help of this segmentation algorithms. Okay, another application that you can think of is the weed detection. Okay, and as I also mentioned, when we can use, once you have detected the weeds, okay, we can use this drones or the sensors deployed on the drones can be used to help spraying the pesticides. Okay, and that is specific to the weeds. Okay, so here we have an example. So on the left hand side we have the original image that we have collected with the help of the drones. Then we have applied a segmentation algorithm, and you can see that these images are segmented as plant and the plant and also as the mud. Okay, then in the end you have applied an algorithm that is built on top of this segmentation for detecting the crop and also the weed. Okay, so in the final image we can see that this weed is identified. That is a combination of segmentation and also a classification. Okay, and finally we can spray the pesticide on specific to the area where the weed is there. Okay, so these are some applications where we can deploy these machine learning algorithms. Okay, in a real time, and this can avoid unnecessary use of pesticides. Okay, and when this is something that we have seen in the original video also. Okay, so now I just move on. Till now I talked about what can be the applications of the segmentation and the classification or recognition algorithm in the context of precision agriculture. Okay, so now I move on to some of the specific algorithms in high level. Okay, so that I mean, if some of you are interested more in understanding, I mean, some of these specifics, you can go and read more about it and make use of these algorithms in a specific problem. Okay. So I wanted to focus. I mean, in the next couple of, in the next few slides, I wanted to focus on the semantic segmentation and the classification algorithms. So that we have seen what are the applications, for example, in the crop detection and segmentation of the area, so that we can do better planting and all these things. Okay. So now I move on to some of the early work that in the literature for semantic segmentation. So the first work that that most people have used for segmentation of the images is based on thresholding. Okay, so the idea is that we divide the image into several regions. Okay, and how we divide the regions. For example, we may use the intensity of a pixel. Okay, and we put a threshold. Okay, and there were several algorithms people were using it for doing this thresholding based segmentation based approach. Okay, but you can see that in all these algorithms we need to come up with the right threshold, so that is not an easy task. Okay, so now people have thought about more advanced algorithms, for example clustering. Okay, so the idea is that so when you consider about pixels, right, so the pixels has a different pixels have different intensity. Okay, and this intensity stands, it stands for different regions in the image. Okay, so what one can think about is that clustering algorithms such as k-means. Okay, so I don't know any of you will aware of this clustering algorithms so far. Okay, so these algorithms are algorithms that help you to group data points. Okay, for example, suppose you have apples and oranges. Okay, and you would like to come up with an unsupervised way to group these two fruits into two groups. Okay, and what you can think of is that you use the color of the fruits, and you use the shape of the fruits. For example, the color of the fruits or maybe the weight of the fruits. Okay, so these are real valued measurements that you take for the fruits. Okay, and based on these two features, you see whether there are some obvious clusters that is exist in the data. Okay, and k-means is one such algorithm. So this k stands for the number of clusters that you specify to the algorithm. This algorithm will automatically come up with a group of data points. Okay, and this is based on some distance based similarity. Okay, so basically the idea is that if you identify a group, all the data points in that group should have similar characteristics. So the distance between the centroid of that cluster and all the data points nearby that cluster should be minimal. So that is the idea. Okay, so the similar idea can be applied here in the segmentation of the pixels also. So we use the intensity as a measure for finding similarity. Okay, and later on people have thought about edge detection algorithms, and there are many geometry based algorithms. Okay, so if you are interested, you can look at this review. Okay, in 2009. Okay, so this the idea is that this edge detection, basically you are interested in the peripherals of a particular area. Okay, so these edge detection algorithms may help you to segment these images. Okay, another set of algorithms that people have used is a graph theory based approach. Okay, these are if you look at all these algorithms, these are before this deep learning era. Okay, so you consider in the graph theory based approach, you consider the pixels are the nodes in the graph representation, and the edges represent some kind of similarity between the pixels. So this can be a score that you come up with the help of intensity, distance, or color. or texture. Okay, so these are the features that you derive from an area of that image. Okay, and you use this graph theory based approach to see whether a group of nodes or pixels are close together or they are representing the same idea. Okay, so in today's class, I mean, I'm not going into the details of the first maybe 4 types of algorithms people have used for semantic segmentation. I wanted to focus more on the latest, I mean, or the state-of-the-art algorithms right now people use for segmentation and also for classification, because you see that some of these algorithms can also be adapted for classification. Okay, and it is called as deep learning based approaches, and algorithms such as convolutional neural networks, and in short form they are called as CNNs. And you also see UNet. It's a specific, or it's a customized convolutional neural network specifically for semantic segmentation. Okay, and the implementations are also available to the public, so you can make use of that in a drawn or other setting. Okay. So before I move on to deep learning based approaches, I just wanted to motivate the idea of so what do you mean by deep learning, or what do you mean by an artificial neural network based algorithm? Okay, so the idea comes from modeling a biological neuron. Okay, so we all know we in our brain we have these neurons. Okay, and these neurons interact each other. Okay, and because of that interactions, I mean, all these decisions are made in the brain. Okay, so in the early 80s or before that, people were thinking about how we can use the idea of neurons. Okay, to build an algorithm. Okay, so where you will have small units. Okay, and these small units are called artificial neurons. Okay, so this artificial neurons works in the same way, or I mean, the idea comes from the biological neuron. Okay, so it has you know, this dendrites. It has dendrites, then it has a nucleus, and this dendrites will collect information from other neurons in the brain. Okay, and it will process it, then it will be transferred through the axon to the other neurons. So that is the idea of this biological neuron. Okay, and in an artificial neuron, people try to imitate this similar idea, but in a mathematical form. So here I have a representation of an artificial neuron. So this artificial neuron takes in inputs. So what are these inputs? These inputs are the features. So I just come back to, I mean, the previous example. We have apples and oranges, and we have measured 2 features that can be the weight and the color. Okay, so you can consider one feature as the color and the other feature as the weight. Okay, and you just plug in these 2 features to the neuron. Okay, and the neuron in the cell body, what it does is that it is using a weighted sum. Okay, weighted sum of these 2 features. Okay, and based on that weighted sum and an activation function. And what is that activation function? So that activation function, you can consider it as a linear activation function, where you consider this neuron as a linear combination of the features you have. Okay, and based on this linear combination of the features and a thresholding in the end. Okay, you can say with I mean, if the threshold is like less than 5 or greater than 5, you are, if it is less than 5, you are coming from class 1, and if it is greater than 5, you are coming from class 2. Okay, so so that is the idea. So so this artificial neuron, you can
I think he has got disconnected, so he will reconnect in a few minutes.
Hello.
Yes, Clint, go ahead.
Yeah, am I audible now?
Yes, you are.
Okay, yeah. Okay, so what I was discussing is about.
But you need to reshare your slides.
Okay, just 1 second. Okay, so I hope you can see my slides now.
Yes.
Okay, thank you. Yeah. So this is like a building block of what is called this artificial neural networks, or and when you have more layers. So in an artificial neural networks, you have this input layer. So you plug in the features. So these features can be the pixels in the context of image classification, and you have an output layer which tells you are coming from which class or the other class. Okay. Then, I mean, based on the number of layers, you can think of more complex artificial neural networks, or it is also called as a deep learning network. Okay, because you are going more deep. You have more hidden layers in the learning algorithm. Okay. So I will skip this slide because this slide is more about how we can make use of this single layer neural network for classifying one type of problem. For example, here we have a classification problem where we can see that you can get a line to classify two types of data points. For example, apples and oranges. Okay, and you see that when you increase the complexity or increase the number of hidden nodes or the hidden layers in a network, you can achieve more complex boundaries as described here. Okay. So I now move on to how we can apply neural networks for the classification problems. Okay. Why this is important? Because this is important for building algorithms that can classify images, and also for segmentation. Okay. So here I have an input image that is a handwritten character. Okay. And based on the neural network, the idea is that you would like to classify the image into any of the 26 English characters. Okay. And the inputs are the pixels, and you have some hidden units. Okay. And these hidden units, inputs and the outputs, are connected with the help of the weights. Okay. And the weights can be considered as the model that you can think of, or the algorithm's parameters. And these parameters are learned with the help of something called a backpropagation algorithm. Okay. So in that backpropagation algorithm, the idea is that we are trying to minimize the error in error in classification. Okay. Or we are trying to minimize the misclassification error. Okay. So that is the idea here. So one of the issues with this deep learning based approach is that when you have a large image, or when you have lots of hidden layers, you will have lots of training parameters, because I mean the training parameters are the weights that is included in the network. Okay. So the question is that how we can improve one such network. Okay. So, and there is also another issue, like the typical neural networks, or this artificial neural networks that we have discussed. It is not able to manage issues such as shifting or scaling of an image, okay, or an object. For example, you are interested in classifying apples, okay, whether it is ripen or not, right? And if your apple is actually twisted, or I mean, because that can happen in a real world setting. Okay. But in these simple artificial neural networks may not be able to handle one such case unless you have lots of data. Okay. So that is something that you would like to improve in the next a couple of slides with the help of more advanced algorithms that I'm going to discuss. Okay. And another issue is that when we think about this artificial neural networks for classification of the images, it doesn't consider the topology of the data or the context. Okay, so when you consider an image or image of a scene, and you see that I mean some of the areas are very similar. Okay, use of that context in the classification itself. So that is not being taken care in the case of simple artificial neural networks. Okay, so we will see an advanced version of artificial neural network or a deep learning algorithm that can capture some of these advanced features, okay, or the context, and also deal with the issues with high dimensionality of the parameters. Okay. So that is what I'm going to discuss in the next couple of slides, and which are called the convolutional neural networks. Okay, so these convolutional neural networks are also motivated, I mean developed based on the motivation of the human brain and how the neurons in the brain are located. Okay, and based on the location of these neurons in one area, when it is I mean dealing with some specific set of tasks. Okay, so I mean that idea is actually make use of when we developed this convolutional neural networks. Okay, so these the idea is that this CNN based algorithms, they can implicitly extract relevant features. So if you I will talk more about this idea in the later slide. Okay, but for the time being, just assume that these algorithms can deal with this I mean feature selection along with classification of the classification of the features. Okay, or the objects that we have in hand. Okay, and here also we make use of this backpropagation algorithm for training the weights or the parameters in the convolutional neural network. Okay, and this CNN can recognize visual patterns directly from pixel images with minimal pre-processing, because that is also part of this feature selection that we do in every classification or machine learning based algorithms. Okay, and you can also see that it's a multi-layer feed-forward neural network, but it has some structure associated with it. That structure will help you to learn some of the contextual information and also issues with higher dimensionality. Okay, so this is the place that I was saying about the traditional classification and CNN-based classification. In a traditional classification, we will have a block that is for pre-processing or feature extraction. So this block we make use of the features that you have measured with the help of some measurements. So this can be the raw images that you have collected with the help of the sensors or these drones. Okay, and you will have to have a feature selection strategy. Then after applying this feature selection strategy, you give that features that you have selected to the classification algorithm, and that does this classification, and it will tell you whether this area is for rice crops or this area is for maybe coconut trees or something. Okay, but in the case of CNN based classification, this CNN is a deep learning framework that will automatically extract features and also deal with issues such as shift and distortion issues that we have discussed. Okay, and also does classification, and we can also see that the CNN can also be used for segmentation. Okay, so I will quickly go over the structure of the CNN. Okay, so you can consider that CNN includes several blocks. Okay, and what are these blocks? These blocks are neurons which are structured in some specific form. Here, for example, the first rectangle stands for the image that you plug in. Okay, so here this CNN assumes that you are actually feeding in an image to the algorithm. Okay, and it applies several layers. For example, feature extraction layer, and it is also called as the convolution layer. Then you have a shift and distortion invariance or subsampling layer, and we have several such layers. So we will have a convolution layer, and after that we will have a subsampling layer. And what are these feature maps? So I will talk more about that. But here I have a picture that explains what is actually a layer that is applied on an image. So here, for example, I have a 32 by 32 image, and here I consider 3 channels, that is RGB, red, green, and blue channels of an image. Okay, and we assume there are several filters that is applied. So these filters are the feature maps applied on that image. Okay, and what are these filters? You can consider that every entity in that filter is like is a neuron. Okay, so that takes in the inputs and it has some weights. So it applies that weights on that the pixels. Then it applies a nonlinear activation function, and finally it gets an output. Okay, so these so what are these outputs? These outputs represent, it's a representation of your input image. Okay, so this representation will help you to extract some features from the in the input image. Okay, so the idea is that each neuron is connected to a local region spatially to full depth. So here you can see that this is a neuron. So this blue neuron is from the feature map. So that is that takes in a region of, it can capture of the context. Okay, and it can also capture several aspects of that context. So that's why there are several such maps layered on top of each other. Okay, and after applying this feature selection, you apply this subsampling layer that I will talk about in the next couple of slides. So this is the general architecture of the CNN deep learning model. It has an input and it applies convolutional layer, subsampling layer, and finally you will have a layer that tells you I mean whether your image is from one class or the other. Okay. Yeah, so here I just wanted to point out that with the help of this feature maps, okay, you can learn the features which may look something like this. Okay, so one feature means exactly I mean what you observe as part of observing a handwritten image. Okay, and the other features that may help you to avoid this rotation and shift problems. Okay, and I mean this is just, I mean I included this image just to compare the original feed forward or artificial neural network with the CNN based approach. Okay, CNN is also a feed forward artificial neural network algorithm, but it has a structure associated with it, and that structure is to capture the context and other features from the data. Okay, so that is the only thing that you need to keep in mind. I mean when we think about CNN based algorithms. Okay. So here I just wanted to explain how these filters are applied on an image. Okay, so and why this name convolve or convolution come from. Okay, so basically you have an image, and with the help of this feature map which has some weights. Okay, so you basically move across the image. Okay, so here we have a 3x3 feature map with some weights. Okay, and these weights are also learned with the help of some learning algorithms. Okay, so by applying these weights, you get some. So when you move this, so this blue is the blue grid is the feature map. When you move from one area to the other. Okay, so you basically learn some features. Okay, so that feature is represented by the output map. Okay, so this map is given to the next layer. Okay, and what is the activation function that you typically use? You use something like a nonlinear rectifier linear unit or something like that. Okay, so these are some functions that help you to learn features from the data. Okay. And the other thing that I wanted to point out, I said that if you use the simple artificial neural networks, then you have lots of weights and or parameters. that makes your learning algorithm complex. Okay, so here since we are in CNN, since we are making use of this feature maps and subsampling layers, so these feature maps the weights are shared. Okay, so all neurons, so here for so here, for example, so here we have an image, okay, and you apply a feature map on that image, okay, and the weights of that feature map is shared, okay, and you can see that that will produce some output, okay, so that is a feature that you have learned, that is represented as a neural net, as a neuron in that feature map, and that is passed to the next layer of the CNN algorithm. Okay, so this way, I mean, since the weights are shared, you can reduce the number of free parameters, and also that will help you to learn better features. Okay, and I just wanted to skip this slide because I mean this basically tells, I mean, how you learn the features. So you have the initial image, and once you apply the feature map, you learn the features with the help of these filters. Then you apply something like the subsampling that I will discuss in the next slide. Okay, so this subsampling layers or the subsampling neural network will help you to reduce the spatial resolution of each feature map. Okay, and this will also help you to achieve, I mean, the issues with this shift and distortion that algorithm for the in a subsampling layer. So this subsampling layer is a layer similar to the feature map layer that we have seen before, and this subsampling basically tries to, I mean, it's also called as max pooling or I mean, max pooling layer. Okay, so basically when you consider a 3x3 subsampling layer, you may take the max of the pixels from that 3x3 map. Okay, so that's the idea. Okay, so that's what you are doing in this image. So you can see that. So the right hand side we have a representation. So that is a subsampled representation of the original image that help you to avoid I mean, this shift and distortion issues in the images. Okay. So so far I discussed about the basic architecture of the CNN. Hello. Yeah, sorry, I think I got disconnected for some time. Okay, so so far I discussed about so far I discussed about this CNN based architecture that can be used for image classification. Okay, so that is one of the popular deep learning based algorithm out there, I mean, that people use, and you can see that when you can use it for image classification, and you will get very good results. Okay, so now I just move on to a setting where I would like to apply this CNN based algorithm for semantic segmentation. Okay, so I mean, this recognition based approaches, we can straight away apply this CNN based the algorithms, but this semantic segmentation, we may have to think this idea separately. Okay, So here, for example, I discussed about segmentation, but here I just wanted to give you more idea. I mean, when we think about a weed separation problem, okay. So here I have an image, okay, that is collected by this Milito and team, okay, and on the top we have an image that is collected, okay, and the idea is that we would like to separate out weeds from the crop, okay, and you can see that how that is done in the end, okay, and this is with the help of a CNN based deep learning network that we have seen in the previous slides, okay. So I just move on to some advanced algorithms that is popular I mean in the context of segmentation, the semantic segmentation, and then I will explain how we can apply in a practical setting, okay. So so when we think about the history of segmentation, okay, so we have seen there were some algorithms which are not based on this deep learning based approaches that we have seen. Then people have seen that this deep learning based approaches are working well in the case of image classification, okay, and they have developed a specific algorithm like CNN, and based on the CNN network, it was performing well in the case of classification. So then people thought about applying this CNN or convolutional neural networks for segmentation problems, okay. So the idea is that so we would like to classify every pixel of an image into a class or not. So that is the idea. But in a typical classification of an image, I mean, you will just classify that entire image into one class or the other. But here you will have multiple classes in the same image itself. So here I have one example. So you can see that we have an image, and you have a dog and a cat. Okay, they are staring at something, okay, and we would like to segment these two, okay. We would like to segment this portion of the image as dog and this portion of the image as cat, okay, and the rest is like the background. So that's what you can see on the right hand side. So you have a segmented image, and one class is for the dog and the other class is for the cat, and you have the segmented I mean background, okay. So that is a different class, okay, and how we achieve this, okay. So I mean the immediate improvisation that one can apply is that you apply this the CNN based architecture. So you take in you plug in this input images, and this input images can be from different channels. So this red, green, or blue channels, okay. Or I mean when you are considering about the drones, right? So you can also consider other channels like I mean that may give you more information. Like you can think about infrared, then you can think about wavelength that may also help you to I mean get an idea about you know the depth of the field or something like that. Okay, so all these things can be given to the CNN based approach. Okay. And here you can see that you start with I mean several such CNN blocks, okay, and you have a forward inference I mean inference architecture, then you have a backward learning. So this backward learning is typically done with the help of this backpropagation algorithm that I have briefly mentioned, okay. So the ultimate goal is that you would like to get a segmentation that you see something like this. So you will have multiple classes in an image, okay. And I mean one of the reason why people have used the CNN is because CNN is able to handle this different input types, okay. So different layers efficiently, okay. And you can also see that the CNNs have fewer parameters, okay. Yeah, so this is one such algorithm that you can think of. that is built on top of CNN for segmentation. Okay, and I just wanted to point out another idea, which is called an encoder decoder architecture, which is built on top of CNN. So that you can also see from this graphical representation. So you have an input image, okay, and it is actually pushed through several convolutional layers. So in a typical convolutional layer, you only have this left-hand side. So it is passed through several filtering layers or feature selection or feature engineering layers, and then it is passed through this max pooling or the subsampling layers. This will help you to avoid any noise, any shift or all these issues, okay, that we have discussed in the previous slides. Okay, then in the end you have you have a portion where you have some representation of the you have a representation of the original image. Then you apply a set of deconvolution network. Okay, so that deconvolution network will help you to avoid loss. Okay, so when you do this this max pooling or subsampling, you are actually losing some information. Okay, so this deconvolution network are introduced to avoid those loss of information that is introduced with the help of this convolution network. Okay, and you will also see that other frameworks, for example, UNet, that is one of the latest algorithms that people use for segmentation. Okay, so in that framework, along with this convolution and deconvolution networks, you will also see that there are some link between different subsampling layers from the convolution and deconvolution network. So this is some way to keep the context and also the things that you have learned from the convolution network can be passed to the convolution network, deconvolution network, and it can give you a better segmentation for the images. Okay. And these are, I know I didn't go into the details of any of these algorithms, but I just wanted to give you in high level how this CNN or an advanced or customized version of CNN can be used for segmentation of the images. Okay, and you see that some of these algorithms are already implemented in many of the popular deep learning architectures. Okay, and it can be applied in an IoT setting or in the case of a drone. Okay, so that I will talk about in the next couple of slides. So now onwards, I wanted to give you some pointers to so how we can, we have seen some algorithms that can be used for image classification or segmentation. Okay, and we have seen that some of these things can be applied for classifying and segmentation. Okay, and this can be deployed in the agricultural domain. Okay, so the first framework that I wanted to describe is the well-known TensorFlow framework that people use for the deep learning implementation. Okay, and there is something called TensorFlow Lite. Okay, so the idea here is that when you talk about this IoT devices, so these are small devices, and their computational if you consider about the capability of that computational capability of those devices, so which are not comparable with the servers or the actual desktop machines. Okay, so what we do is that typically these classification models or the segmentation models that we have seen, or these deep learning models, so which are trained with the help of a large data set. Okay, and and with the help of the servers or the GPU servers or the CPU servers. Okay, and so this learned or the trained network then will be deployed in an IoT device. Okay, and I mean, this TensorFlow Lite is a framework that help you to do that. Okay, and you can see that I mean, if you look at this framework, you can see that this will help you to deploy this CNN based classification frameworks on your mobile, or you can also I mean, apply that on a Raspberry Pi or similar devices which can be deployed in the farming industry. Okay, and I will give you one example in the end of this talk. Okay, and this is one thing that you can think of, and I mean, this is for classification. Okay, and I also mentioned about segmentation. Segmentation, I mean, you can see one example here. So we are interested in segmenting the people inside people in the scene that you have seen. Okay, so we would like to segment the background and person. Okay, with the help of the algorithm. Okay, so in the TensorFlow framework, they have implemented a segmentation algorithm that is called deep lab. Okay, so this deep lab is also also a customized convolutional neural network. Okay, and it is one of the latest algorithm that is popular for segmenting images. Okay, and it is implemented in the TensorFlow Lite, and if some of you are interested in deploying this in an IoT device, that will help you to do that. Okay, and yeah, and this deep lab also make use of some of the probabilistic concepts that people have used before the deep learning era for segmenting images. Okay, and it is called the conditional random fields. Okay, and I mean, you can see that in all these these slides, I am not going into the details because I thought this is, I will just give you the high level view of how we can apply these algorithms and what are these algorithms which are popular in this context. Then if you are interested, you can go into the details. Okay, yeah. Yeah, so here, so how much time I have? So I have 15 more minutes. Okay, so I will give you one example where people have used this TensorFlow Lite for classifying or detecting diseases from the yucca or cassava plantation. Okay, so
the important crop it provides. The important crop it provides for over 500 million Africans every day.
When all other crops fail, farmers know that they could rely to provide them food. There are several diseases that affect cassava, and these diseases make the roots unedible. It is very crucial to actually control and manage these diseases.
So we're trying to use machine learning to respond to those diseases. And
TensorFlow is the best foundation for our solutions. The app that we've designed can diagnose multiple diseases. It's called Nuru, Swahili for light, the light that farmers can use to see their problems and find solutions. You wave your phone over a specific leaf, look at it, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, we have an option for you to get advice and learn about the best management practices.
The object detection that we use through TensorFlow relies upon our team annotating images.
We've collected over 5,000 high-quality images of different cassava diseases for this project. We use a single-shot detector model on a mobile net architecture. It's able to make predictions in less than 1 second.
Instead of having to implement thousands of lines of code, TensorFlow provides a library of functions that allow us to build architectures in much less time.
We need something that can be deployed on a phone without any connection. TensorFlow is able to shrink these neural networks to be able to fit on your mobile device.
The human...
Yeah, so in this video, I mean, you have seen how this TensorFlow based classification algorithm that can be used to detect certain diseases. Okay, but in the context of this IoTs or flying drones, okay, I mean that is deployed in a field. You can consider that these images are taken with the help of these IoT devices, okay, or the sensors, okay, and you can apply these I mean this CNN based algorithms on the on the drones, or I mean the data can be collected at first, then it can be processed in the server level, then it can be the reports can be generated to identify whether a particular disease is actually infected in a particular area. Okay, so that is one example that you can think of.
The important crop it provides.
And I just wanted to give you one last example where we can apply this machine learning with the help of something like this NVIDIA Jetson. So it's a toolkit that is provided for teaching, learning, and developing AI and AI algorithms and robotics. Okay, and I just wanted to point out a couple of examples where people have used this NVIDIA Jetson, okay, in the farm industry. Okay, for example, this rabbit tractors. So it's a swarm farming startup. Okay, so they uses this AI for efficiency and sustainability of farming. Okay, so the idea is this. So so they have developed a set of robots. Okay, and these robots are used for spraying, then weeding, and also for seeding. Okay, and it can also be used for harvesting. Okay, and it runs. I mean, it runs on electricity, so it is lightweight and low cost. Okay, and these devices are connected or communicated through a wireless network. Okay, and it includes several cameras and some lidar sensors. So these cameras are used to collect images from the field, and the lidars are used to detect detect the depth of the field or something like that. Okay, and this supports real-time object detection with the help of this deep learning frameworks that can be deployed on these devices. Okay, so this includes this NVIDIA GPU processors. These processors can be used to better inference. Run better inference algorithms. Okay, and these tractors are something like this. It has 4 wheels, and this Jetson is deployed in each of these tractors. Okay, and it's a group of tractors, and you can see that in a setting like this, it cannot actually communicate with the server. So there is a network that they have constructed with the help of these devices, and they interact each other, and making use of this low cost IoT devices, they can better predict, okay, and navigate in the field. Okay, and here I have another example, and it's called FarmWise, and they run this GPU powered autonomous weeding machines, and it is deployed in California, US. Okay, so they have several cameras, and it captures the pictures of the weeds. It's similar to what we have seen before, and this also uses this NVIDIA. So if you are interested, some of you can look at this this device, and it's not that costly. Also, it's also available in the Indian market. Okay, and we can deploy this in the field, and you can use this TensorFlow or similar machine learning or deep learning frameworks that can be deployed in in devices like this, and it can be used for improving farming, and and it can be used for precision agriculture. Okay, so I stop here, and if you have any questions, I can take it now.
Good afternoon, sir. Am I audible?
Yeah, you are audible. Yeah.
Uh, yes, sir. Very good afternoon. Thanks for the informative session. I just wanted to know whether there is any time limit in which I can make use of a Jetson Nano in a particular system. Like if you are employing Raspberry Pi in a system, it will not run for more number of hours. But is there any limitation of Jetson Nano that you need to use it for only several hours? Otherwise, it will fail.
So maybe I can I can give you more. I mean, explain this in the case of an algorithm implementation. Okay. So typically, when you think about a device like this, you are not planning to use this for a large-scale learning. Okay. So ideally, in a farm environment, right? So you collect the data and you learn the model. Okay, and you may be using this model for adapting what you see in the field. Okay, so basically, I mean, you can also think about a setting like a transfer learning approach. Okay, so you have a model that you have trained with the help of the data that you have collected over a period of time. Okay, and you may be using servers or other complex machines for learning the network. Okay, and these devices can only be used for the inference. So I mean, and maybe some adjustments to the parameters that you have learned. So in that case, you can reduce the computational overload and also the power consumption. But if you are asking some specific questions about the architecture details, I don't think I'm not the right person to answer that question. Yeah. So maybe Sharad can, yeah.
So if your question was how long can a Jetson Nano board run, right?
Yes,
I think that was your question. So
yes.
Jetson Nano doesn't have a battery supply. It needs a connection to a power socket. Okay. So normally if you are using a Jetson Nano board on say a mobile platform, say as an example, the tractor that you see in this image, okay, so there will be some source of power supply on that tractor, and then that power supply will provide power to the Jetson Nano board so that it keeps running. Okay. Otherwise, you will have to develop a power supply, a small scale power supply to power up the board and keep it running. Okay, and now how long it will run? If it is connected to a continuous power supply, it can run as long as the power supply is there. Okay, but if it is connected to supply from a battery, then of course it depends on the capacity of the battery and how much current your design is draining while it is running on Jetson Nano. So these are the factors which will affect how long the board will run.
Thank you, sir. Sir, I have one more query. Can you suggest any tutorial or any simulation tool where I can learn more about Jetson Nano?
I think, I mean, if you just search for this Jetson Nano in YouTube or in Google, right? So you will be redirected to that, I mean, this NVIDIA's website, and they also provide some development tools, okay, and also some videos, okay. So how you use this Jetson Nano, okay. So I think it is very informative. I think that is that may be the first place to start.
Thank you, sir.
Yeah.
But the most important point is, you see, a Jetson Nano board costs around 10,000 rupees. Okay. So the important thing is that if you could buy a board like that, then you buy it and then you start playing with it. So unless you implement something on it, unless you get familiar with the tools that are used for programming on Jetson Nano, okay, because it is from NVIDIA, so there are some CUDA libraries also available for Jetson Nano and all. You will not get a hang of it, but once, like in the 4 sessions that were held yesterday and 3 yesterday and 1 day before yesterday, it is this hands-on thing which is very important. to actually understand, how implementation can be done and what factors should actually be taken into account.
Thank you, sir.
So any other question from the participants? So this talk was more about a case study or an application of IoT in a particular domain. How you can use IoT based, how you can in fact combine IoT based sensors and other things on a flying drone or on a robotic platform, and then perform, somebody asked in the earlier session, analytics. Perform analytics on that, and then based on that analytics, you do some action, right? Otherwise, if you don't have to, so in commercial deployments or in real deployments, there has to be some action that needs to be taken.
Yeah.
Once the analytics is done. If you stop at visualization, then that is only for academic purpose. You can visualize, you can see, but unless you use it to take some decisions, to make some, choices, uh, that is when your actual deployment would happen. So things like there was a video that showed robotic arms that are picking up cherries or strawberries or even the other fruits, apples and all, and so that is through image processing of those fruits through the small scale image sensors that are there on the robotic arms or something like that, and then some actuation is happening in that robotic platform whether to pick that fruit or not. So these small scale things you can also do in your lab, in your institutes or college lab. You can buy very simple robotic platforms, and then you can combine an Raspberry Pi with it. On Raspberry Pi you can run, Raspberry Pi also comes with camera, so you can run simple algorithms for image processing and all, and then based on the feed that camera provides, you process it, and then Raspberry Pi actuates, say, some hand or some small robotic platform, to do some action. So this kind of tutorials you will also find on this website, which has a lot of such projects. Okay. So any other question? So generally you would not, cluster of RPI, you see, when you design the robotic platforms that you saw, which are working in the field, these are not, the companies which provide those solutions, it is not like they have one solution and they say it can be deployed everywhere. They have a base solution, but then they will customize it for your field, for the farm that you have. Okay, so maybe, and the kind of fruit that you want to purchase, sorry, that your robotic platform will pick. uh, so based on that, they will suggest whether it should be, one cluster, one RPI or multiple RPIs, based on how much data you want to acquire. That will depend. And an RPI generally in this case would serve as data acquisition. RPI with combined with the sensor would serve as data acquisition, data transmission platform, and then that data would be transmitted either to some cloud, or it can also be pushed to a storage uh, hard disk or something like that, on that tractor itself. And then at the end of the day or at the end of the operation, you can take that hard disk or that laptop, whatever it is on that tractor, and you can analyze the data. So these are different ways in which a solution can be rolled out or implemented in the field. Okay. So it is not like one solution fits all. That approach doesn't work. the base idea, the base concept, the base box in all these solutions would be same, but then for the actual on-field deployment, some customization, some addition, some removal may need to be done. And in fact, these days, even when you buy a laptop, you can customize the laptop, right? So compared to a laptop, this is a much more complex system. So Clint, you can answer this question.
Yeah. So yeah. Okay. Yeah. So I think yeah, I understand. I mean, because some of these things, this data set for an agricultural domain. So, I mean, I would recommend you look at some of these references that I have used in the slides. Maybe I will also share that slide with you, Sharad. So, so that I mean, some of these papers are talking about the data sets that you can use, but some of these specifics, for example, detecting the weed from the I mean, weed along with this crop, right? So that is, I mean similar data sets, it's very hard to find because these are specific for a particular crop. And for the Indian setting, I mean, I think it's very hard to find out real data sets. Okay, but you also need to keep in mind that, I mean, if you have a I mean, camera enabled device like a cell phone, right? You can collect I mean, images of these I mean, the disease plants and normal plants, and you can straight away apply I mean these algorithms that is available. Okay, so that is another way to, I mean, to get started. I understand that I mean, to get started with similar algorithms, you need data sets, but some of these data sets you can collect it I mean, with the help of cell phones. I mean, this is something that I have seen, I mean, when I search for data sets online in the Indian context. Okay. Yeah, and publicly available data sets, I think University of California, Irvine, they have a repository of machine learning data sets, but it's not very specific to the agricultural domain. So these are some challenges that that you have, and I think there is one website where you can buy these images, but that is collected by a private agency. Okay. That if I find that link again, I will send it across. Yeah.
So I'll just add to that point. So UC Irvine dataset is there. Then there is there is a very popular platform called Kaggle, which is for data science and related competitions are held on this platform. So you will find data sets there also, agriculture related data sets. Okay, and then there are some other data sets available. If you just do a Google search, you will find it. But a lot of these data sets are available on Kaggle. Okay, and you see Irvine dataset is a good reference to at least start doing some work. So you will find their dataset related to the specifications of flowers. So flowers have petal and sepal, so the length, width, etc. And then based on that, how you can classify whether a flower is of type this or of type that. So those kind of tasks can be done by using the data set which Dr. Clint mentioned is available at on UC Irvine website. Maybe I'll put it in the chat box, that data set. This one. So any more questions?
Yeah, I think Kaggle has some data sets for agriculture. So, but that, I mean, but that may not be for the images. So, by the way, this CNN can also be used to non-image data. So that is also another thing that you can keep in mind.
Okay, so I've shared the attendance link. If anyone missed in session 1, you can fill it up. It has to be filled only once during the day. Okay, the session wise attendance I take from Microsoft Teams. So then, if there are no further questions, then I would like to thank Dr. Clint on behalf of myself, IIT Goa, and all the participants for this interesting session on applications of IoT in farming. And tomorrow you will have a session on IoT for smart transportation systems, and in the morning. Then today in this at 2:30 you have a session on simulation for IoT, how to simulate IoT systems. Okay. So then on behalf of everyone, I will thank Dr. Clint one more time, and we will end this session and see you all at 2:30. Please use the link for session 3 to join the session.
Yeah, thank you, Sharad, again, I mean, for giving this opportunity to talk about this. And thank you all for joining. Okay, thank you.